Hi, welcome to my channel, Math Made Easy with Laurel. I'm Laurel, and in this video we're going to look at using the basic logarithmic form to do integration. So in the last video we talked about the general power formula, which allowed us to integrate a function u to the n du, where u could be an algebraic function or a transcendental function. And we were able to integrate that. The integral is 1 over n plus 1, u to the n plus 1. And if it's indefinite integration, we put plus c. But there was a very important requirement: n could not equal -1. In today's formula, we're going to look at the case where n is equal to -1. Before I do that, I just want to review something with you. Let's let y equal the natural log of u. I'm going to differentiate with respect to x, so dy dx will be 1 over u du dx. Okay, that's on our formula sheet with all our derivatives of our transcendental functions. And then I'm going to multiply through by dx. So dy will equal 1 over u du. Now what I'm going to do is I'm going to integrate both sides. So the integral of dy will be the integral of 1 over u du, and the integral of dy is simply y. So y is equal to 1 over u du. I'm just going to rewrite that as the integral of 1 over u du is equal to y. Remember what y is equal to? It's equal to the natural log of u. So this gives us our basic logarithmic formula. The integral of 1 over u du will be equal to the natural log, and I'm going to put absolute value of u because you can't take the log of a negative value. So we're just going to put the absolute value in there, and we're going to add our constant of integration for indefinite integrals. So this is called the basic logarithmic form for integration. Another way you can think of it, 1 over u is the same as u to the -1. So now we have a formula for u to the n if n is equal to -1. Let's take a look at some examples. So I've just got the rule listed here that we're going to use. I also have my list of derivatives of transcendental functions handy. And when we look at our first example, you might want to rearrange this so it's in this form. You might also want to move any coefficients out that aren't part of the du factor. You don't need to. But I'm going to write it as 1 over u, so 1 over 2x cubed minus 1. And then what I have left is x squared. I'm just going to put that at the end and hope that it's part of my du factor. So I'm identifying this as 1 over u. Therefore, u is 2x cubed minus 1, and du dx will be 6x squared. So the du factor will be 6x squared dx. Do we have the du factor? Well, we have the most important part of it. We have the x squared. We can introduce a 6. As long as we are multiplying by 6, we also divide by 6. So now that I have it of the form 1 over u du, I can integrate, and this will be 3/6, which is 1/2, times the natural log of the absolute value of 2x cubed minus 1 plus c. Let's take a look at the next example. Again, I'm going to separate these. So I'm going to write it as 1 over tan of 3x times secant squared of 3x dx. So this is my 1 over u. So I'm identifying u as the tangent of 3x. We look up the derivative of tangent of a function, and that derivative will be secant squared of that function times the derivative of that function, which is 3. So the du factor will be 3 times secant squared 3x dx. I have secant squared 3x dx, but I don't have the 3. So I'll introduce it and then balance it. So this is my du factor. Now it fits my pattern, 1 over u du. So my integral will be 1/3 natural log of tan of 3x. Put the absolute value signs around it, plus c. So you might have to do a little bit of manipulation in order to identify that that's the pattern you're going to be using. Let's take a look at some more examples. In my next example, I'm going to write it in this form. So I'm going to get my 1 over u separated. I can pull the 2 out front of the integral sign. And then I'm going to write it as 1 over 1 plus 3 e to the 3x. And I'm left with an e to the 3x dx. And I'm hoping that this e to the 3x is part of my du factor. So I'm identifying this as my 1 over u. So u is 1 plus 3 e to the 3x. Again, I don't write 1 over that. I just want the u. The pattern is 1 over u, so u is just 1 plus 3 e to the 3x. I find the derivative will be 0 plus 3 e to the 3x times the derivative of 3, which is 3. So the differential will be 9 e to the 3x dx. When I look at my du factor, I have the most important part of it, but I'm missing a 9. So I'll introduce that as long as I balance it. Now that I have my du factor exact, I can use this form. So I'll have 2/9 times the natural log of 1 plus 3 e to the 3x plus c. You may notice I did not put my absolute value sign here. I didn't forget it, but I only put the absolute value sign if it's possible for the function to be negative. In this case, it doesn't matter what x is. X can be positive or negative. E to a negative value is still positive. And when I'm adding it to a 1, it's still going to be positive. So there's no way this function can ever be negative. So if you notice that, you don't need to put your absolute value signs. All right, let's take a look at our next example. Again, I'm going to separate this 1 over 1 plus 2 times cos of 5x times sine of 5x dx. So if that's 1 over u, u is 1 plus 2 times the cos of 5x. The derivative will be 0 plus 2 times the derivative of cos of 5x is negative sine of 5x times the derivative of 5x, I'm using the chain rule, which is 5. So the du factor will be negative 10 sine of 5x dx. I have sine of 5x dx. I'm missing the negative 10, so I'm going to multiply by negative 10 and divide by it. So now that my du factor is exact, I plug into my rule. So it's going to be negative 1/10 times the natural log of 1 plus 2 times cos of 5x plus c. Let's do some more. In our next example, we have a product here. Do not multiply that through. It turns out that one of these things is going to be the derivative of the other function. So remember that if this is my u, the derivative of 4 plus natural log of x will be 1 over x. This is a 1 over x. So let's split this up. And recognize that this is my 1 over u, not the other way around. So u will be 4 plus natural log of x. The derivative of that will be 0 plus 1 over x. So the differential is 1 over x dx. So it's important to be aware of what the derivative of these transcendental functions are so that you can recognize this sort of thing. So that's my du factor. Now I can integrate this. 1 over u du will be the natural log of u, of the absolute value of u, plus c. In our next example, we don't know how to integrate a quotient. We can't do 1 over u because this is not going to be the derivative of x cubed. But what I am going to do is break up those terms to be 3x squared over x cubed plus 5 over x cubed. When I simplify, I'm going to get 3 over x plus 5 over x cubed, which I can think of as 5 times x to the negative 3. I know how to integrate a term like that. And now, because of this rule, I know how to integrate that. You might want to break up each term because we're using a different technique. So you might want to break this up into integrals like this. You could pull the coefficients out front if you want. Now let's integrate this. So it will be 3 times the integral of 1 over x dx is natural log of the absolute value of x, plus 5 times the integral of x to the negative 3 will be x to the negative 2 divided by negative 2, plus c. Let's clean this up. It would be 3 times the natural log of the absolute value of x minus 5 over 2x squared plus c. So these integrals can be very difficult. You'll encounter some function you're not sure how to start, so you might have to play around algebraically. Or you may need to use some trig identities. We'll take a look at doing that in the next example. In this last example, we have sine of 2x in the numerator, and we have 1 minus cos squared of x. So you might recognize right away that we have different angles. So one thing you can do is use your identities right off the bat to replace both sine of 2x as well as 1 minus cos squared x. So if you look up your double angle identity for sine of 2x, it's equal to 2 sine x cos x. In addition, your Pythagorean identities say that cos squared x plus sine squared x equals 1. So therefore, sine squared x will equal 1 minus cos squared x. So we're going to replace sine of 2x with this, and we're going to replace 1 minus cos squared x with this. So we're going to have 2 sine x cos x over sine squared x. Then what we're going to do is cancel a factor of sine x in the numerator and the denominator, and we can pull the 2 out front as well. So we're going to get 2 times the integral of cos x over sine x dx. Then what we're going to do is separate this so that we have 2 times the integral of 1 over sine x times cos x dx. Now we have 1 over u, where u is sine x. The derivative of sine x is cos x. So the du factor will be cos x dx. And we have that. So we can integrate this. This will be 2 times the natural log of the absolute value of sine of x plus c. Also realize that with properties of logs, this could be expressed as the natural log of sine of x squared. That's the third property of logs. So we're bringing in trig identities, we're bringing in properties of logs, and be aware of that so that if your answer is different than the answer you look up, you understand why and how you can manipulate it to get it in the other form. So as usual, practice these as much as you can. The more practice you get, the better you'll be. And the next video is going to be on another form or pattern of integration called exponential form. So when you're ready, I'll see you then.